So what we have here is we have a cantilever beam, which means that this side is fixed and this side is not supported, and there's no other supports in there. And on this end we have an 8 kilonewton per meter distributed load, and then on this end we have a 6 kilonewton point load. And what we need to do is we need to find and draw the shear and moment diagrams for those. And so that's what we're going over in this video. If you want a video explaining shear and moment diagrams, you can click on this video link, and also down in the description I've written out all of the steps for writing shear and moment diagrams. And so if you find this video helpful, hit that like button and please subscribe. It helps me out a lot. So the first thing we need to do is we need to draw our free body diagram, and then we'll solve for our reaction forces. And so here we have our beam, and then on this end we have our point moment or point load of 6 kilonewtons, and on this end we have our distributed load and 8 kilonewtons per meter. Over here we have our reaction forces, we'll call it A sub y, and then our moment reaction here, M sub A. And the way we're going to solve for those is with equilibrium equations. We'll say that the sum of the moments about point A equals 0 because it's in equilibrium. And then we have this 8 kilonewton meter force. The center of gravity is 0.75 meters away from point A. So 0.75. It's 1.5 meters long times by 8, that's 12. And since it would cause clockwise rotation about point A, we will say that it is negative. And then as well, with the 6 kilonewton load, it is going to cause clockwise rotation, so we'll say it's negative. We have 6 and it is 3 meters away, so multiplied by 3. And then we have our reaction moment here. And we've drawn it going counterclockwise, so we'll say it's positive plus M sub A. So now we solve for M sub A, and it equals 27 kilonewton meters. And then we'll label that right here. This is 27 kilonewton meters. And then we'll sum forces in the y direction. A equals 0. So we have, once again, 8 times by 1.5. So that's 12. We'll say it's negative because it's pushing down, or minus 6. And then we have our reaction force, A sub y. And then so add that up and we get that A sub y equals 18 kilonewtons. And we'll relabel that right here. And the reason why we're not solving for the forces in the x direction is because there wouldn't be any, there's not any forces acting on it in the x direction, and so there are no reaction forces in the x direction. So the next thing we're going to do is we're going to draw our shear and moment axes right below our beam, so we can help line ourselves up with those. And then we'll want to label them. V for shear, and we'll label the units, kilonewtons, and then for our moment, kilonewton meters. Okay, so the first thing we want to start off with the shear diagram is we have our reaction force here of 18 kilonewtons. So that's going to jump our graph up to 18. And then the area under the curve is the change in the shear diagram. So the area under this distributed load is our change in our shear. And because it's pushing down, it is going to drop our the line on our shear diagram. It's going to go down. And so 8 times by 1.5, that's 12. So it's going to drop it we're considering this negative area, so it's going to drop it down to 6. And so we're going to kind of mark here where this distributed load kind of ends on both of these axes, and it's going to go from here to here. Just draw a line. Because this is a flat distributed load, we're going to have a constant slope on the diagram. And then for the rest, nothing changes between here and here, so it's just going to be a straight line across that. Nothing's going to change until we get to our 6 kilonewtons, and it's going to drop it down back to 0. We were at 6 right here, and we came and we dropped down to 0, and that's one indication that we have done it right, because at this end there's no support reaction, so it's got to end back up at 0. So moving on to the moment diagram, we have a reaction moment here at the end, which is going to either start our moment diagram up high or down low. And we called this a positive moment earlier because it's turning in the counterclockwise direction. But that is the reaction of the wall, or whatever's holding this beam. It's what's pushing back on the beam, keeping it from rotating. So the internal forces, which is what we're mapping here with our shear moment diagrams, they're doing the opposite. They're reacting the opposite way. So just like these forces are pushing down, our shear diagram went up, or is going up. The shear inside the beam is positive, reacting against the shear pushing down on it. In the same way, our moment diagram is going to drop down because this is a positive moment, so the internal bending moment inside the beam are pushing in a clockwise direction, and we'll say that's positive. So it's going to start down here at negative 27. This is a negative slope on this line, so we know that our slope here on this is going to be concave down. You need to find the area under here, but we know it's positive area, so it's going to go up. And so we have 6 times by 1.5, that's 9, and then 12 times by 1.5 is 18, divided by 2 is also 9, so the area under here is 18, so it's going to go from 27 plus 18, that goes up to 9. So we have it goes to negative 9. And so we'll draw a point here. There's nothing changing in here in our shear diagram besides that function line, so it's going to look something like that. It's concave down, it goes up to 9. And then here on our, draw that a little straight, we have just area under the curve here, and so the area of that is 6 times by 1.5, that's 9, and so we're going to have, because this is positive area, it's going to be going up on our moment diagram in from a linear function, so it's going to go something like that, and end here at 0, right, because we're at negative 9, and the area under here was 9, so the change in our moment diagram is 9 kilonewton meters, and so it's going to go up 9, which ends at 0, which is what it needs to be because there's no reaction force here, so it can't end at anything other than 0. So that is our diagrams. So if you didn't understand any of that, you can once again watch the video of me explaining all of the shear moment diagram stuff, and there's another link at the end of this video you can click on. The steps are also down in the description. I think you'll find that pretty helpful. I've also been creating some awesome designs with the student engineering logo, like the one on this t-shirt, and been putting on t-shirts and hoodies and stickers and mugs and stuff. And if you want to buy some of that, the links are down in the description. Go buy them on Amazon and Teespring, and if you do, that helps me out a lot. So if you're new to this channel, my name is Preston Palmer with Student Engineering, and my goal is to help other engineering students like me better understand this crazy engineering stuff. So if you find this helpful, hit that like button and don't forget to subscribe.